let's talk about the individual shapes then. We got ourselves to the point where we found out that the number of different sub-level shapes is equal to the value of the principal quantum number. First energy level, n equals 1 has one shape, n equals 2 has two shapes, blah, 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 blah. What are these shapes? Okay. If you can turn to page 105. I think I'm close. Okay, that's not bad. That's not bad at all, but I'm wrong. Go one more. Boom. Actually, there's a couple of different things that we're going to look at on this page. First of all, did I mention anything about that 90% probability region? Where the size of an orbital is defined as a 90% probability region of finding an electron. It was related to the two questions towards the end of that little worksheet, okay? I said technically an electron for any one atom could be found anywhere in the universe. Well, that makes for a pretty big atom, okay? So we have to hone that in a little bit and define that, and so we look at a 90% probability region. So if you look at that at the top of page, is it 107? Yeah, top of page 107, over on the left-hand side, you will see, by the way, that is the shape of an s orbital, which you would describe that as, don't say circle. Yes. Very good, circle. Okay. Anyway, that would be, notice how it's darker in the middle, and then as you go further away, it gets lighter and lighter and lighter. What that, again, is trying to represent is a probability of finding the 1 or 2 electrons in a 1s orbital. Now, we have to, at some point in time, like I said, limit that, so the drawing on the right represents that 90% probability region. Everyone hunky-dory there? Mm-hmm. Okay, well, so once again, that is the shape of an s orbital. Over on the lower right-hand page, I'm not doing it exactly, clearly, exactly as the drawing on the bottom right is, but what the bottom on the right is trying to show you is the general distance from the nucleus for each of the energy levels. Notice that there's a large gap between the first and second energy level. Would you agree? Mm-hmm. And then as you go further and further away, those energy levels become closer and closer to each other. There's a reason for that, which we won't get to until we get to chapter 5. But the reason I'm pointing that out now is we're going to start seeing some issues as we start putting the electrons in the orbitals, and I'm just trying to set you up for that. I wanted you to notice that diagram. Okay, so that's an s orbital. It's spherical in shape. Flipping over, looking on at the bottom of page 108. Once again, you'll see an s orbital lined along the 3 axes in space, and then in the middle, the green, that is the shape of a p orbital. Okay? And then over next to that in the whatever orangish kind of colored that might be, that is one shape of a d orbital. We'll get to more of this later. But anyway, so we say a p orbital actually has 2 different lobes. So we have a node here. Does anybody remember the word node? Either from physical science or what we did back there. Yeah. Okay, so we have a node, and then we have a 90% probability region that has like 2 lobes. And so the electron could be anywhere within those 2 lobes. For lack of a better word, many of my students over nearly 3 decades ago we decided to call this shape a dumbbell shape. Got anything better? Yeah, most people are pretty satisfied with that. Okay? Okay. You know, I can probably show this to you. You can call it whatever you would like. Now, And again, you see one of the d orbitals over on the right-hand side there. What page am I looking for here? No, 327. Just want to verify. Now, as it turns out, most textbooks, your textbook does not, but if you see one of the AP books nearby, and it looks like there's a number of AP books nearby, if you turn to page 327, some of you guys might have to share a little bit. We seem to have a high concentration of AP books over here, so I'm going to steal one of these. Nicely done there, Alan. And kind of distribute that over here so you guys can kind of... But anyway, on page 327 in the AP book, you'll see some representations of the f orbitals. What shape do you guys want to call those? Yeah, I got nothing on that. We're just going to call it F. That would be an F shape. You do not have to know the shapes. However, I will tell you this. For the S's and the P's, we're actually going to rely on those shapes to do some other things later in the unit and even into the next unit. So you'll get, spherical and a dumbbell, so you can do that. All right, anyway, moving on. We are now done with the orbital quantum number. Did I go over the values of L that were possible? Did I do this with you?
Yeah.
So now we have N, which can equal all the positive integers through infinity. The values of L can be and I have to do this. I just thought of it. A L of 0 represents an S orbital. Did I do this with you guys? I do not think I did. An L of 1 represents I think you guys can figure this out, a P orbital. An L of 2 is a D, and an L of 3 is an F orbital. It was somebody in my other class. Someone in my other class says, what comes after F? I'll ask you, what comes after F? And that's exactly right. So from that point forward, we in this class are never going to deal with those, okay, for reasons that will come up a little bit later. But if you were to evaluate them, they would just follow the alphabet after that. O, G, H, I, J, okay.
What about when you get to...
I'm sorry, what?
Like, do S and P with P, or do you just, like, skip over those?
You're about to find out. Okay, so, moving on. We have that covered. Ish. And now it's all going to start coming together, I hope. Well, next is what we're going to call the magnetic quantum number. Let me put it up there. Which we're going to use an M sub L for its symbol. And the magnetic quantum number indicates the orientation of the orbitals about the 3 axes. Of course, you guys already know the 3 axes that are X, Y, and Z. This is always a fun little question to ask. For purposes of us being able to communicate with each other, we are going to draw the axes in the way that you're used to drawing the axes, with the X on the horizontal axis, the Y on the vertical axis, and the Z and the, well, perpendicular to both of the other two, okay? But, I mean, honestly though, what's an atom doing at all times? Moving, spinning, they're always, moving around. So when I ask Elisa what the x-axis is, let me see, how am I going to do this? There we go. If I ask Elisa to touch the x-axis, where would you touch? Just go ahead, take your pencil and reach right out there. X-axis, there you go, good. And if I asked Rowan what the x-axis, she would say, no, you would not. You failed geometry, didn't you? You would say this one, right? Wouldn't you? Okay, so they just touch two different axes. How is that possible? Well, it depends on your perspective. Now, let me ask you where the x-axis is. And whatever, okay? So, in order for us to communicate with each other, we're going to designate them the way we normally do, but you have to remember that, what is the x-axis? I remember with my freshmen, always used to do this, I always had a globe in my old room, and every time for whatever the reason, I'd get it out like 5 or 6 times for different things. But anyway, one time, the first time I would ever get out the globe, I would always have it, and you guys would say upside down, right? And I'd get it out, and I'd be pointing at different things. They'd, like 8 hands would be up. Mr. Lehman, it's upside down, it's upside. No, it's not. It's up. And so then I said, okay, and then I turn it sideways. I go, there, that's better. And they said, no, now it's sideways. What's up? What's down? Do you really know? It's a fun thing to think about. So all those little creatures that live in other parts of the universe, what's up? What's down?
Nothing much.
What's new? Excellent. Okay, anyway, so indicates the orientation. S orbitals have one orientation. I mean, how many different ways can you orient a sphere about the 3 axes in space? 1. Okay, p orbital. Well, there's 3 axes in space, so there are 3 orientations. The d orbitals actually have 5 orientations, and the f's have 7. Which means we now get to go fill in more of the little ladder that we have. So at n equals 1, we have an s orbital, and there's only one s orbital. However, at n equals 2, we have that same type of shape, orbital, an s and a p, but as I just got done saying, there are 3 p orbitals. Each of those orbitals is aligned, as you can see in page, I think that's back on 107 still in your books, or 108? No, 109. 109, at the top of page 109. Showing each of the p orbitals, one aligned along the x, one along the y, and one along the z. You are, for this class, going to need to differentiate between the x, the y, and the z. I am not going to have you differentiate between the 5 different d's, and definitely not have you differentiate between the 7 different f's. Okay? So anyway, wherever there's p orbitals, there's going to be 3 of them. Now the d's, and remember the first place you're allowed to run into a d is the 5th energy level. What we're going to do, since I'm not having you differentiate between them, is just put like a little bracket underneath those. Once I teach you the quantum numbers for the magnetic quantum number, we will get to how we're going to be able to differentiate amongst them. And then clearly there are 7 Fs. You just have to know that there's 7 Fs. And so there we go. Now, the possible values for M sub L are negative L through 0 up to positive L. This is where things start getting a little interesting. I think everybody's been hanging on pretty well so far. Everything's kind of making a little bit of sense. This is where it gets fun. So, for example, anytime, remember we talked about if you know all 4 quantum numbers, we know exactly where an electron is?
Yeah.
Turns out each electron that exists in an atom has its own unique set of 4 quantum numbers. We're about to learn that. There's a little principle that's named after here in a little bit. Okay? So when I give you some information regarding the quantum numbers, it's referring to an electron. So, if n equals 2 and L equals 1 and M sub L equals 0, what does that mean? Well, I'm about to show you. Okay? Because at n equals 2, what are my possible values of L? Could either be 0 or 1. I erased it. Look on your sheet. Remember, for L, it ranges anywhere from 0 through n minus 1. If n is 2, what's 2 minus 1? 1. So 0 and 1 are my possible values for L. Now look how that makes sense. I just got done showing you that an L of 0 represents an s orbital, and an L of 1 represents a p orbital shape, right? Okay? So if n equals 2, my possible values for L are 0 and 1, or in other words, S and P. Okay? I'm designating which one. So what shape orbital is this electron? Well, it's at the second energy level, and it's in a p orbital. L equals 1. That's a p orbital. Okay? Now, which p orbital is it in? Well, if L equals 1, what are my possible values for M sub L? Negative 1, 0, positive 1. Watch this. Negative 1, 0, positive 1. See where I'm going with that? So in this particular example that I'm giving you, where's that electron? In the py orbital. I know, that's the first time in your life you guys ever seen this before. Your brains are kind of trying to make sense of it. It takes a little while. You'll get it. You're all going to get this piece. Not all of you are going to be able to relate that to the actual quantum numbers as well as others. That's normal. That's okay. All right. Let me see. Where else do I want to go? Oh, here's a couple of interesting fun facts. I think this one's down there. I never mentioned this on the orbital quantum number. So if you want to add this to there. I think I did tell you this, actually. the number of sublevel shapes is equal to the quantum number? I think I told you that, didn't I? To the principal quantum number? N equals 2, there's 2 shapes. N equals 3, there's 3 shapes. Okay, here's a fun fact about the magnetic quantum number. The total number of orbitals is equal to n squared. So at any one value of n, the total number of orbitals is equal to n squared. It's going to be cool. You'll see it here in a second. Total number of orbitals is equal to n squared. So at any value of n, the total number of orbitals available at that energy level is equal to n squared. So let's think about what all n tells us. First of all, it tells us which energy level we're on. N equals 3. What energy level? Third energy level. At n equals 3, how many differently shaped orbitals are allowed? 3. What are those shapes? S, P, D. See where I'm going? So that n equals 3 gives us 3 different ideas. It tells us which energy level, it tells us how many differently shaped orbitals, and I just got done saying, it also tells us the number of orbitals at that energy level. What's 3 squared? 9. How many orbitals are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Isn't that cool? At n equals 5. Which energy level are we at? 5th. How many differently shaped orbitals are there? 5. Just for fun, not that you'll ever be quizzed or tested on this. What are those orbitals? S, P, D, E, sorry about that, F. S, P, D, F, G. Right? Remember we played around with that? So that's what they would be. Just for fun, how many orbitals would there be? 25. Interestingly enough, I think you guys are, a couple of you guys are smart people, so you're noticing the trend, okay? How many G orbitals would there be? 9. You're noticing the trend? 1, 3, 5, 7, 9. Okay. All right, moving on. What else do I want to do with this? So in some ways, just so you guys see this, this would be a -1, this would be a 0, this would be a +1. Oh wait, we're not even done yet. You guys will just be flat out amazed here in a little bit. Your jaws are going to go. It's going to be cool. All right, and I think, you know what, do I want to do this now? No, I do not. Lastly, any questions before I move on? Because it's going to go away. You have a lot of questions, I know, but it's just a matter of, we got to put it together, so let's do that. And the last one is what we call the spin quantum number, which is represented by the symbol m sub s. It's all right. Don't worry about it. It's only a $180 book. Who cares? No, I'm messing with you. I hope I started this video. Okay. Spin quantum. Hey, anyone want to take a stab as to what the spin quantum number represents?
how it spins.
How about how the electron spins? Now, watch how I do that. This. I am not. Well, I might be. Nobody really knows.
I mean, I'm going to believe whatever you
I get that. I get that. Don't always do that. But where I'm going with this is, no one really knows if I'm telling you the truth or not. No, seriously.
Yeah.
No one knows. We're about to get to that. Notice I put the word spin in quotation marks. Has anyone ever seen an electron? No. The answer is no. You can't. Because in order to see the electron, you're going to have to send some energy towards it. And when you send energy towards it, it's going to cause it to go somewhere else anyway. So you're not even seeing the darn thing, okay? So what am I talking about the spin? We don't know if they're spinning or not. However, they do behave as if they were spinning. I don't think anybody, no, I know no one in here because I've asked you about this. It's possible at some point in time, if you get into enough physics classes, that you might take a class on electricity and or magnetism. Okay? Have we talked about the left-hand rule in here yet? You have no idea what I'm talking about. Okay. What is electricity? We've already talked about this. Electrons moving from one place to another. Usually we try to get those to go along a certain path called a wire. Okay? Anyway, electromagnetism, the two properties are related, very closely related to each other. Anytime you get electrons, or electricity, moving through a wire, okay, it induces a magnetic field. You may or may not be aware of that. That's a lot of reasons why there's a couple of reasons, but one of the reasons why your wires are coated with something is to try to reduce the amount of that, okay? But anyway, if you take your left hand and point your thumb in the direction of the current, okay, so let's say the electrons are going this way, I point my thumb this way, my fingers curl in the direction of the induced magnetic field that it's producing. Those moving electrons induce or cause a magnetic field. Okay? Now, as it turns out, any charge that is spinning also induces a magnetic field. Now, can anyone think of a charged particle that spins? Well, you're currently residing on one. Most of you. Earth?
Oh, yeah. You know that thing.
That thing. Okay. Most of you reside. Okay, we're still worried about Josh, but he pops in now and again. Anyway, so if you take this electric charge and again with your left hand, curl your fingers in the direction of the spin, it induces a magnetic field such that your thumb points to the north pole of the induced magnetic field, and obviously the bottom of your hand would then be the south pole. Okay? So if you take your fingers and curl them in the direction of the spinning object that has a charge, like say an electron, it induces this magnetic field. Okay? This is the evidence that electrons spin, because as it turns out, they behave as if they were spinning. They have induced magnetic fields that they have generated. I know, it's pretty heavy, okay, to think about, but it's going to all make sense here in a second. Guess what two types of spin we're going to look at or consider? It's not that hard. Well, if that thing worked, it would be spinning in a certain direction. And counterclockwise, yep, clockwise and counterclockwise. So, remember, we're talking about quantum numbers. Here's the two quantum numbers for spin, clockwise, counterclockwise. Wait a minute, those aren't numbers. Okay, so I'm going to show you the numbers here in a second. Clockwise spin represents positive 1/2. Counterclockwise represents negative 1/2. There's your quantum numbers. Okay? But I'm going to show you here in a little bit, it might not be today yet, that even writing positive 1/2 and negative 1/2 to represent each electron is going to get to be a really pain in the rear end. So what they do is use the symbol of an arrow pointing up to represent clockwise spin and the symbol of an arrow pointing down to represent counterclockwise spin. Oh, really? If I spin my fingers, which direction is that? And where's my thumb pointing? Up. That's why it's got an arrow pointing up. Okay. Now, here's what's interesting. Here's a point. Each orbital is allowed 2 electrons that must be of opposite spin. So each of the individual little orbitals is only allowed to have a maximum of 2 electrons. But those 2 electrons, if they're going to be in an orbital together, have to be of opposite spin. Why is that? Well, first of all, do electrons want to be next to each other anyway? No, because they're like charges. Like charges have a tendency to repel. However, they can tolerate each other if they have opposite spin. Okay, so because that way, currently we already talked about my fingers spinning in the clockwise direction with the arrow pointing up, right? Please hold out your left hand, Alyssa, and do this. Great. Okay. Now, this is always fun. It happens every year. What I would like you to do, there's no way these 2 electrons are going to hang out to each other. First of all, they're both negatively charged. Secondly, even though they are negatively charged, if they were to get close to each other, we've got North Pole next to a North Pole, South Pole next to a South Pole. What's that going to cause? More repulsion, right? So reverse the direction of your fingers. Excellent! That doesn't happen very often. Usually I get kids that go like this. They try to bend their fingers. Okay, everyone see what she did. Now, they're still both negatively charged. Okay, they don't like each other that much. However, they can tolerate each other now because now we've got North Pole, South Pole, South Pole, North Pole. They can kind of like when you shared a room with your siblings, if you ever had to go through that. Did you ever have to go through that? Did you tolerate each other? Did you repel on occasion? Yeah, these things happen. Okay. So you were able to occasionally be close to each other. Yeah. So one of you flipped over, right? Is it younger or older sibling? So you flipped her over. Just kidding. Did that happen? No? Okay. Did you ever share a room with one of your brothers?
Yeah.
Do you still share a room with one of your brothers? No. Did one of you flip the other one? Yeah. Okay, moving on. So, now, let's do the math on this, everyone. Let's do the math. Let's imagine n equals 2. What energy level we're referring to? Second energy level. How many differently shaped orbitals are at n equals 2? 2. S and P. What's the total number of orbitals at n equals 2? 2 squared is 4. But each of those orbitals is allowed to have how many electrons? 2. Therefore, the total number of electrons is equal to 2n squared. The n squared is the number of orbitals times 2 electrons per orbital. Would you agree? This is the number of electrons per energy level. Quick and dirty way of doing that. So now we have two phrases that Mandy does not like. Plug and chug and quick and dirty. Which means estimate. Okay, so let's try that. You guys are going to love this. First energy level. How many electrons?
2.
Well, 1 squared is 1 times 2. 2. Second energy level. 2 squared is 4 times 2. 8. Does this sound familiar? How many electrons are the first energy level allowed to have? 2. How about the second energy level? You've known this for a while, haven't you? Now you know why. Now, up until this point, I said, well, third energy level, we're just going to go with 8 for now, but you may remember me saying later we'll look at or 18. Does anyone remember that? Me saying that?
No, I don't.
Okay.
No.
Third energy level, how many electrons? 18. Fourth energy level? 32. Seventh energy level?
98.
98. Look at you guys go. Never even knew about the seventh energy level, did you?
No.
You kind of did. You knew of the existence of it.
Not really.
How did you know of the existence? Alyssa? Yes, but how did you know there were 7?
I don't know. Didn't you say they can be anywhere?
How many periods on the periodic table? 7. What do the periods represent?
How many orbitals they need?
Energy levels. Oh, wait, people, it gets better. It gets better. How much time do I have? Okay, this will be the thing that will blow your mind. We'll leave it at this, and then we'll come back and play with this a little bit tomorrow. Okay? First of all, looking at your periodic table, and I'm going to keep popping over here. Okay? First energy level is allowed to have how many electrons? 2. What orbital is being utilized? An s orbital. At the second energy level, how many electrons are allowed? Or how many different orbitals? Well, there's 2 different shapes. There's 4 orbitals total, right? Notice how this has 2 families, 2 groups over here, right? These are known as the s orbital filling groups. Because how many electrons are allowed to go in an s orbital? 2. How many p orbitals are there? How many electrons in each orbital? 2, for a total of 6. 1, 2, 3, 4, 5, 6. These are known as the p orbital filling groups. How many d orbitals? 5. How many electrons per? 2, for a total of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the d orbital filling groups. And how many f orbitals? 7. How many electrons? 14. Now, remember, these 2 electrons or atoms here go here, right? You guys know that. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Those are the f orbital filling groups. Oh, we haven't even started yet. Isn't that cool? Yeah, it's so amazing what we're going to get out of that periodic table and where the elements are on that period. The information that is embedded in the positions of the elements on the periodic table. So I can do an electron configuration. What was the example I had given up there? I said n equals 2, L equals 1, M sub L equals 0, right? I'm telling you right now, that element was either nitrogen or neon. Because we're at L equals 2, or sorry about that, N equals 2, L equals 1, which puts us in a p orbital, right? But we're talking about M sub L of 0, which was the, oh, I lied, it was either carbon or fluorine. Okay? And the reason I don't know whether it was carbon or fluorine is because I never told you what M sub S was, whether it was positive 1/2 or negative 1/2. Right? If it was positive 1/2, it would be carbon, and if it was negative 1/2, it would be fluorine. Oh yeah, it's all going to come together tomorrow. It'll be fun. All right. Oops. Excuse me.
Sorry, man.
All right. Nicely done, people.